Welcome to the video for Lecture 18, Section 3. This video is about feed-forward control. Be sure to remember that when I say feed-forward control, I really mean feedback plus feed-forward control. Feed-forward control is used to improve a slow or sluggish process. Many large processes have time constants that are many minutes long. With such a slow process, it takes a long time before one of the inputs is manipulated to correct the process output. By using feed-forward, the manipulated input is adjusted sooner. With feed-forward control, we measure some load input characteristic. That measured input characteristic is then used to adjust the manipulated process input sooner. The sketch here shows a large heat exchanger where steam is used to heat water. This is a common industrial process. The temperature of the heated water is adjusted by manipulating the steam flow rate. In many cases, the steam temperature can vary, so it makes sense to add a temperature sensor to the input steam line and use that temperature to adjust the steam flow rate so that the heat exchanger can do a better job producing the water at the desired set point temperature. The steam temperature adds feed-forward control to the original feedback control system that measures the heated water temperature to adjust the steam flow rate. This slide shows a block diagram for the normal feedback loop that we solved in Section 12 of the course packet. There are two changeable inputs. One is the set point R, the second is the load N. This block diagram describes our steam heated heat exchanger process 2 if we use only feedback control. If we add feed-forward control, we get this block diagram. This block diagram describes a steam heated heat exchanger with feedback and feed-forward control. The process output variable is T and the load input variable is T subscript I. In the block diagram, we have the normal feedback loop that includes G1, G2, G3, and H, and the load input N. In the block diagram, we have the normal feedback loop that includes G1, G2, G3, and H, and the load input N. To add feed forward, we add a sensor to the input load T subscript I and a transfer function G5 that sends the feed forward output to a summing point that produces the process signal P. This is a good time to note that the reason this is not the same as cascade control is because the loop is not measuring an internal process value somewhere in the primary feedback loop. With feed forward control, the sensor is located in some input outside of the primary feedback control loop. We want to find the overall transfer function for this feedback plus feed-forward control system, T over T subscript I. We begin by writing the transfer functions. Starting on the right, we write T equals M times G3. M equals Q plus T subscript I times G4. The next equation is Q equals R minus T times H times G1 times G2 plus T subscript I times G5 times G2. The last term, T subscript I times G5 times G2, is the feed-forward part of the equation. Combining the terms produces the equation at the bottom of the slide. After some algebra to simplify the equation, we get the equation shown here that describes the process output T as a function of all the transfer function elements and the two process inputs T subscript I and the set point R. Here are two Laplace domain equations describing closed-loop process control systems. The one on the left is the equation for feedback only. The equation to the right is the equation for feedback plus feed-forward. The difference between the two equations due to feed-forward control is the G5 times G3 times G2 term in the numerator of the second term multiplied times the measured input T subscript I. That extra term provides the feed-forward element. This brings me to the end of the Lecture 18 Section 3 video. Write down any questions you have and bring them up in class or lab.